Hello everyone, in this video we would be explaining the concept of automatic control systems, and then we'll use an example, that is example 2.24, to solve this problem. So it states that we should find the damping ratio of a space vehicle attitude control system. The goal is to assume that the time constant of the controller is 3 seconds, and then the ratio of torque to inertia to be 2/9 rad square per second square. So we are supposed to find the damping ratio.
So my name is Oliver Lodikwako. So the problem statement is to determine the damping ratio of the space vehicle control system. The damping ratio tells us engineers how quickly oscillations die out in the system, and it is a key measure of system stability and then the transient response quality. So to approach the solution, we need to find the open loop transfer function G of S, form the characteristic equations that we will need, and then compare them with the standard second order form, calculate the damping ratio. And in the problem statement, or in the diagram given, the time constant was given as 3 seconds, and then the gain ratio is given as 2/9.
Hi everyone, my name is Yvonne Deizanga, and I'll be continuing from where they ended. So then for this part, we are finding the forward path transfer function and finding that we have a controller that's CS, that's K TS plus 1, then there's a plant, and that one T is 1 out of JS square. And the plant converts the torque input to angular position output, and the controller provides the gain and adds a 0 at S equal to 1/T to improve stability. So then multiplying the controller and the plant, we get the forward path transfer function. So it will be G of S equal to K TS plus 1 out of JS square.
Hello everyone, my name is Gideon. So I'll be continuing from where my peer left on. So in this part, I'll be explaining unity feedback, which is equal to H of S equal to 1. So for the general closed loop form, there's 1 plus G of S times H of S, which is equal to 0. So from here, we substitute H of S, which is equal to 1. So it will become 1 plus G of S equal to 0. So then we also substitute G of S, which is also equal to 1 plus K to bracket T of S plus 1, all divided by JS squared, which is equal to 0. Thank you.
Hi everyone, I'm Winnie Charles NG. In this step, we are going to eliminate the denominator. So to do that, we are going to multiply through by JS squared. That will give us JS squared plus K multiplying TS plus 1 is equal to 0. And that further simplifies to JS squared plus KTS plus K is equal to 0. Now we are going to divide through by J to convert the equation into the monic form. And that will give us S squared plus KT on J S plus K on J is equal to 0. Now this version of the equation becomes easier to compare to the standard second order system equation.
Hello, I'm Ifraj, and I'll be talking of the standard form comparison. So we divide the equation by J, and then we get S squared plus KT on J, or S plus K over J is equal to 0. And then for control systems, the standard form of a second order system is giving us second S squared plus 2 zeta omega ns plus omega n squared is equal to 0. So we then compare it with our previous equation. We get 2 zeta omega n is equal to KT on J, and then we get omega n squared is equal to K on J.
Hi everyone, my name is Sebas. I will be taking the step where we have to find the natural frequency omega n. So since we know the value of K over J, which is equal to 2/9, I'm matching it from omega n squared, which is equal to K over J. Omega n squared is equal to 2/9. Therefore, if we are to find the square root, omega n is equal to the square root of 2/3.
Alright, so now we compute the damping related coefficient Kt of J using the given values of T and K on J. This equals to tau omega, which we will use to solve for tau. Now we have our time constant to be 2 seconds. We have K on J to be equal to 2 on 9, giving us our KT on J to be equal to 2 on 3.
My name is Musa Mohammed and I'll be taking you through the damping ratio calculation. So substituting the value omega n into the equation 2 zeta omega n, which is equal to 2/3. From previous steps, we already derived the values for K over J, which is equal to omega n squared, which simplified gives us omega n equal to the square root of 2/3. And Kt over J is equal to 2 zeta omega n, which is equal to 2/3. So substituting now, we get 2 zeta brackets square root of 2 all over 3 brackets close, which is equal to 2/3. Making zeta the subject and solving for zeta, we get zeta is equal to 1 over square root of 2.
Hi everyone, my name is Fahad Aruna, and I'll be taking you guys through the final stage of the example. Under the final answer, we have 0.707, and then it's a second order system, whilst the damping type is underdamped. The stable is a stable system, and then the K oscillation as its response. Thank you.